It's lesson 3 video and our final video for first semester. Wrapping up probability for us. We're looking at binomial and geometric random variables. So these are two types of random variables. Remember, we talked about a random variable being a variable that represents a chance process that has values that are possible outcomes and probabilities associated with each. Those probabilities are very similar to frequencies that happened with each that we looked at in chapter 1. So here I want you to keep in mind what the difference is between binomial and geometric random variables, and how can we use each to determine probabilities. So that encompasses the requirements for checking what they are, as well as the calculator functions associated with each. And just a quick note, quite often these will pop up on the AP test. So I would predict that there'll be a binomial free response question on the AP test this year. So what they do is they count a number of successes and a fixed number of trials. So what the thing is that the probability of success on each trial has to be the same. So the applications where we've looked at pulling a card out of a deck and not replacing it, where the probability changes of getting a heart, let's say, on the first and the second draw, don't apply, because the probability of getting a heart changes if you don't put the card back in the deck. So the probability has to be the same when we have a situation where we have a huge number we're pulling from. So 52 cards is not a large number, but if we're pulling from a population of like 1 million and we pull one and don't replace it, so the probability just changes slightly, then we can use a binomial calculation to estimate it. So an example is counting the number of times something happens in a random sample from the population. So a sample size of 10 from a shipment of 10,000 CDs, the number of defective CDs we'd get. Now we have a large enough sample size here where we can ignore the fact that pulling one slightly changes the odds. So binomial, we have to check bins. Binary means there's only two possible outcomes, a success or a failure. In the example of CDs, it's defective or it's not. Independent, each trial must be independent, so one should not affect the next. Number, meaning there's a fixed number of trials advanced in the process. And success, the probability of trials and success of each must be the same. Now, these two, I and S, independent and success, can be the same, but occasionally they can be different, meaning so we have to check both, because sometimes things are independent but the probability of success on each trial isn't the same, or vice versa. So prior to using a binomial calculation, we have to always check these. And for you, as you get used to using these concepts, it'll be key to check these in order to make sure it's a binomial setting and not a geometric setting, which we're getting to next, or perhaps neither. Mistakes involving identifying binomial distributions are one of the most common errors on the AP. So if you don't know how to answer a probability question, quickly think, is this binomial? Check bins. So we're counting the X number of successes in a binomial setting. The probability distribution of X, it's a binomial distribution where N is the number of trials and P is the probability of success on each trial. Values of X are the whole numbers from 0 to N. That means we're looking for a number of successes. So the X flips, the value of X could be anywhere between 0 and 6. So we're trying to see how many successes for the number of heads. So obviously you can't have more successes than the total number of flips. That's what we're saying here. P representing the probability of heads on each of those. With a fair coin, that'd be 1/2. So essentially a binomial calculation is like a shortcut to a large tree diagram. So instead of doing a tree diagram, once we have the basis and understand that tree diagram, we can use this binomial calculation as basically a way to calculate all that without having to draw it out. Now, drawing it out is really key to understand what it is we're talking about and what the probability means, that it's a series of different outcomes and we add the probabilities together. So the binomial coefficient, the binomial calculation is helping with this. So if we want to say the number of ways, like for example, getting 3 heads on 6 flips, there's a variety of ways we can do that. We could get on the first 3, the first 2 in the 4th, the first 2 in the 5th, the first 2 in the 6th, and a variety of others. So this coefficient shows us how to arrange a certain number of successes, K, out of a certain number of trials. So 5 choose 2 says how many ways can we have combinations of 2 successes out of 5 trials. So you could have the first and second, first and third, first and fourth, first and fifth. You could write all those out to check it. Your calculator can do that for you. And on page 388 it shows you it. Now one thing I want to point out, this is not related to 5 over 2 or 5 times 2. In this case it happens to be 10, but it's not related to 5 times 2. It could be K could be the number of shots made out of a number of attempts. If we looked at like Steph Curry and how many times, the probability of him making 25 out of 30 attempts, the way we could arrange those 25 successes. So right now pause and check the tech corner on 388 for learning how to do that with your calculator. One important note as you do that is that binomial PDF is for when x is equal to a specific value, just the way normal PDF was for equal to a certain value. We will occasionally use that, whereas normal PDF we didn't tend to use it because we didn't want to see, we're usually interested in interval, meaning a variety of values in between two numbers, which is when we use BinomialCDF. So the probability for less than or greater than equal to a specific value. So the calculator will show you less than or equal to. If you want greater than or equal to, you're going to need to use the complement rule, which will be critical for your free response coming up. So remember the complement rule being 100% minus the value, since BinomialCDF gives you less than or equal to. So pause now for your free, or pause after I explain. Here's your free response. I want to know what's the probability of getting at least 3 5s in the next 6 rolls. Use the binomial calculator function to figure this out. First, think about what's the probability of a 5 with 2 dice. I'll give you the first example, a 1 4. What other combinations could add up to it? You have 36 possibilities because there's 6 possibilities on each die. So I gave you the first. How many total ways could you roll a 5? That's the probability of success. Now we're looking at BinomialCDF NPK. The number of trials here is 6. Our probability of success you need to figure out. And now K is going to be interesting because remember BinomialCDF tells you less than or equal to. But we want to know at least 3 5s. So what's the complement of at least 3? Pause. Plug that in. Look over the calculator function in your book. And then start playing the video again, please. So here we're talking about mean and standard deviation of the binomial random variable. That's where our expected value equals the number of trials times the probability. This would be like saying if you're an 80% shooter and you took 100 shots, n would be 100, probability would be 0.8, we'd expect you to make 80, or 80 out of those 100. The standard deviation, so that's pretty intuitive. The standard deviation is the square root of the expected value times the complement of the probability. So that one's a little more challenging. Now check your formula sheet to locate those. This can only be used for binomial distributions and can't be used for others. So now here's the condition I was talking about for probability. So we can use a binomial distribution to model the count of successes as long as n, the sample, is less than 10% of the total population. So we can't sample more than 10% of the population or we tend to lose independence and our probabilities or calculations don't hold up. Okay, a geometric random variable, we're going to be looking at the number of trials until we get 1 success. So the key difference here is a binomial random variable. We're looking at the probability of getting a certain number of successes and a fixed number of trials. Here we're saying what's the number of trials until we get 1 success. So how many 3-pointers will Steph Curry have to take until he makes 1 of those 3-pointers? That's a geometric setting. A binomial setting would be looking at a fixed number of trials and saying about a number of successes within those. So geometric is looking for the number of trials y that it takes to get to 1 success. So we look at bits here, that it's success or failure, so the same as before. Independent, one outcome does not affect the next, one trial doesn't affect the next. That we're counting, t is the difference here, we're counting the number of trials until the first success, and s, the probability of success on each must be the same. So same conditions, which is nice, except for t, meaning we're counting the number of trials to 1 success. That's what makes it geometric, not binomial. So here's some more key information about that. Geometric probabilities on your calculator. There's geometric CDF and PDF, where CDF is a cumulative function, counting the number of the outcome of a variety of the combination of a variety of outcomes, adding them all up, and PDF for the probability that y equals k. Here we have page 400, which you should check on how to use it with your calculator. And then the mean. So the mean is equal to 1 over p. So let's talk about it in a simple situation like flipping a coin. The number of trials we'd expect until we got 1 heads. Well, the probability heads is 0.5. 1 over 0.5 is 2. So we'd expect 2 trials on average before we got a heads, which makes sense. Okay, now's a good time to pause, look over the summary of the lesson in your book for 6.3. This tends to be a bit more challenging, so getting a handle on the conditions, the calculator functions, and what it is we're really talking about with geometric and binomial is key here. So take a look over the summary, look over those definitions and examples, and then decide which one of these is a geometric setting. Pause now and then submit your answer on the form below.